Japan is spending tens of billions of dollars to build a railway where the train barely touches the track. It will travel at around 500 kilometers per hour, connecting Tokyo and Nagoya in roughly 40 minutes, and eventually, Tokyo to Osaka in about 67 minutes. But this isn't simply a faster Shinkansen. Most of the route will run through tunnels, while superconducting magnets lift and propel the train. The project is so expensive that its cost estimate for the Tokyo-Nagoya section has now reached about $67.7 billion. So, why is Japan building it? The Chuo Shinkansen is Japan's biggest attempt to reinvent high-speed rail. JR Central's current plan uses superconducting magnetic levitation with a design speed of 505 kilometers per hour. But the real story isn't just speed. It's the enormous infrastructure required to achieve that speed. Tunnels through mountains, underground stations, massive guideways, and a completely different propulsion system. To understand why Japan is spending so much, we have to start with the problem this railway was designed to solve. Japan's Tokyo Shinkansen is one of the world's busiest high-speed railways. It connects Tokyo, Nagoya, and Osaka along Japan's main economic corridor. But the line has been operating for more than 60 years. At the same time, passenger demand and train frequency are already extremely high. That creates a strategic problem. If something seriously disrupts the Tokyo route, a huge part of Japan's transportation network could be affected. Earthquakes are another concern. Japan sits in one of the world's most active seismic regions, and the country has to prepare for large-scale disasters. The Chuo Shinkansen was therefore planned as a second major transportation artery between the three metropolitan regions. Instead of simply adding more trains to the existing route, Japan would build a completely separate high-speed corridor, and speed would be its biggest advantage. The planned fastest journey from Shinagawa to Nagoya is around 40 minutes, compared with about 86 minutes on today's Tokyo Shinkansen. Eventually, Shinagawa to Osaka is expected to take about 67 minutes, compared with roughly 134 minutes today. That means Tokyo, Nagoya, and Osaka could effectively operate as one much more connected economic region. But achieving those travel times requires something conventional rail cannot easily provide. The train has to operate at around 500 kilometers per hour. And that is where magnetic levitation enters the story. A conventional Shinkansen depends on wheels touching steel rails. The Chuo Shinkansen takes a radically different approach. Its superconducting maglev system uses powerful magnets to levitate and guide the train above the guideway. At high speed, there is no conventional wheel-to-rail contact carrying the train. Instead, superconducting magnets on the train interact with coils installed along the guideway. Those magnetic forces provide levitation, guidance, and propulsion. The result is essentially a train moving through a controlled electromagnetic system. But the magnets are only one part of the technology. The superconducting system has to operate at extremely low temperatures. The guideway has to be manufactured and installed with enormous precision. And the propulsion system has to coordinate with the train as it moves through section after section of the route. Japan's testing program has already demonstrated extraordinary speeds. The L0 series reached 603 kilometers per hour during testing. But commercial operation is planned around a maximum design speed of 505 kilometers per hour. That difference is important. A test train can chase a record. A commercial railway has to operate safely and reliably every day. And that means Japan isn't simply building a faster train. It is building an entirely new railway ecosystem around magnetic levitation. But there's a major reason the project costs so much. The train is only a small part of it. The real megaproject is hidden underground. The biggest surprise about Japan's maglev project isn't actually the train. It's where the train will run. A huge portion of the Shinagawa-Nagoya route will pass through tunnels, including deep mountain sections. The most difficult example is the Southern Alps Tunnel. The planned tunnel is about 25 kilometers long and reaches depths of roughly 1,400 meters beneath the surface. At that depth, engineers aren't simply digging through ordinary soil. They are dealing with complex mountain geology, groundwater, pressure, and difficult access. Tunnel construction therefore requires different methods depending on the ground conditions. In urban areas, shield tunneling machines can excavate underground while maintaining stability around the tunnel. A massive cutting wheel rotates at the front of the machine, breaking the ground and carrying the excavated material away. Behind the cutting head, concrete segments are installed to form the tunnel lining. The result is a continuous underground structure built while the machine slowly advances. But mountain tunnels require a different approach. Engineers have to understand the geology ahead of the excavation and carefully manage groundwater and unstable rock. And this is where the project's enormous cost starts to make sense. Japan isn't simply laying tracks across open land. It's drilling through cities, mountains, and some of the most technically difficult terrain along the route. The tunnel system also needs emergency access, ventilation, drainage, power, communication, and safety infrastructure. So every kilometer underground becomes a complete engineering project. And after all that excavation, there is still another problem. The train needs a guideway accurate enough to support a vehicle traveling at around 500 kilometers per hour. That's where the railway itself becomes a giant precision machine. A conventional railway uses two steel rails. The maglev uses something completely different. The guideway contains the coils that interact with the superconducting magnets on the train. These coils aren't simply passive pieces of metal. They form the electromagnetic system that guides and propels the vehicle. As the train moves forward, the interaction between the train's superconducting magnets and the guideway coils creates the forces needed for high-speed operation. This means the infrastructure has to be extremely precise. A conventional train can physically follow a rail. A maglev depends on electromagnetic forces to maintain its position relative to the guideway. Any major irregularity could affect that relationship. So engineers have to control geometry, alignment, structural strength, and long-term stability. The guideway also has to survive temperature changes, earthquakes, and decades of repeated operation. And then there's the enormous amount of electrical equipment required to operate it. Power must be delivered to the correct sections. Substations convert and manage that electricity. Control systems coordinate the train with the infrastructure. In other words, the guideway isn't just a track. It's part of the propulsion system. That completely changes the economics of the railway. A conventional train carries much of its propulsion equipment on board. Here, a significant part of the technology is built directly into the route. So every kilometer of railway contains sophisticated infrastructure. And that explains why this project is so expensive. But there's another engineering challenge waiting above the guideway. At 500 kilometers per hour, air becomes a powerful force. And Japan has to make sure the train can move through it safely and efficiently. At 500 kilometers per hour, the train isn't just fighting friction. It's fighting the air. As speed increases, aerodynamic resistance rises dramatically. That means the shape of the train becomes extremely important. The nose has to be carefully designed to move through the air efficiently. This becomes even more difficult when the train enters a tunnel. A train traveling at extreme speed pushes a huge volume of air ahead of it. Inside a confined tunnel, that air has nowhere to escape easily. The pressure can create powerful aerodynamic effects around the train and at tunnel entrances. So engineers have to design the train and tunnel as one system. The vehicle's shape helps reduce pressure changes. The tunnel geometry has to provide enough space for airflow, and the entire system has to remain comfortable for passengers while the train accelerates and decelerates. There is another major challenge. A maglev train doesn't simply follow a pair of rails. It has to remain precisely aligned with the guideway using electromagnetic forces. The superconducting magnets on the train interact with coils installed along the guideway. Those magnetic forces help keep the train centered and provide the propulsion needed for high-speed operation. At low speeds, conventional wheels are used during certain phases of operation. But once the train reaches the required speed, it transitions into levitated operation. The train then moves with almost no physical contact between the vehicle and the guideway. That eliminates the wheel and rail contact that limits conventional high-speed operation. But removing physical contact doesn't make the railway simple. It makes the infrastructure more sophisticated. The train, the guideway, the power system, and the control network all have to work together with extraordinary precision. And that raises the final question. After spending trillions of yen on this technology, what does Japan actually gain? The Chuo Shinkansen isn't being built simply because Japan wants the world's fastest passenger train. Its purpose is much larger. The railway is designed to create a second high-speed transportation artery between Japan's largest metropolitan regions. The existing Tokyo Shinkansen carries enormous passenger volumes and has been operating for more than 6 decades. The Maglev provides another route between Tokyo, Nagoya, and eventually Osaka. That creates additional transportation capacity. It also provides another major connection if the existing corridor is disrupted by a large natural disaster. JR Central describes the project as part of its long-term preparation for aging infrastructure and major disasters, including the Nankai Trough earthquake scenario. And then there is speed. The planned operating speed is around 500 kilometers per hour. That could reduce Tokyo, Nagoya travel to about 40 minutes. Tokyo, Osaka could eventually take about 67 minutes. But achieving those numbers requires an enormous investment. The currently planned Shinagawa, Nagoya section has a construction budget of about 7.048 trillion yen, while the full Tokyo, Osaka project is estimated at about 9.03 trillion yen, including rolling stock. That money is paying for far more than trains. It's paying for tunnels, bridges, stations, guideways, power systems, and an entirely new transportation technology. The maglev is therefore less like buying a faster train, and more like building a completely new transportation network from the ground up. And when you finally step back, the scale becomes clear. Japan isn't simply trying to make trains faster. It's rebuilding the way its biggest cities are connected. For more than half a century, the Shinkansen changed how Japan moves. Now Japan is attempting another transformation. A train that levitates. A guideway that becomes part of the motor. Tunnels stretching beneath mountains. And speeds approaching 500 kilometers per hour. The most impressive part isn't the train itself. It's everything that had to be built around it. Because at this speed, the railway cannot simply be a pair of tracks. It has to become an integrated machine. And if Japan succeeds, Tokyo, Nagoya, and Osaka will be closer together than ever before. Not because the cities moved, but because the time between them became dramatically smaller. That's the real power of the maglev.